Hi everyone, my name's Adam Shephard and I teach within the Department of Computer Science at the University of Warwick. And I hope this talk today is going to give you a bit of an introduction to how computers see and a bit of a taster of the module image and video analysis within computer science. So if you've ever wondered how you can open your smartphone using just your face, or how autonomous vehicles manage to stay in their lane, or how AI is really advancing medical imaging, then hopefully this module will give you the starters to focus on these technologies. But first of all, we're going to start by discussing what is an image. And what you see here is a lovely sunny day, as it always is at Warwick. And this is our piazza. You can see lots of people milling around. And your brain, which is this sort of marvel of billions of biological neural networks, managed to process this instantaneously and subconsciously, so you can recognize these objects, people, places instantly. Whereas a computer essentially sees this sort of large array of pixel values, essentially, this big spreadsheet of pixels ranging from 0, which is black, to 255 generally, which is white. So this module is about teaching you how we take these large amounts of pixel data and turn them into sort of meaningful scenes that computers can understand. And to do that, we're going to start by discussing the human visual system. Because if we can understand the human visual system, then it's much easier to understand computer vision. And also, there's lots of parallels between the human visual system and computer vision. For instance, how we see with our eyes and how we acquire images with cameras, but also how we process images in our brain and how computers process images. And as I say, our eyes and our brain manage to recognize objects instantly. But there is, however, some quirks and some limitations to the human visual system. And you'll probably recognize some of these things, such as optical illusions. So on the left here, we have this series of parallel and perpendicular lines that look to you to be sort of converging and diverging when they're actually not. And on the right, you have these train tracks with these lines that seem to be of different sizes, but actually they're the same length. And these here are optical illusions. And you'll find out why these optical illusions exist if you were to take this module. But as a brief explanation, our brains have evolved over millions of years to essentially process an image and to understand it really, really quickly and efficiently. And so it takes shortcuts at times. And this sometimes leads to mistakes or errors or optical illusions. And us as computer scientists, if we can understand some of these things, then we can actually design better computer vision systems that aren't necessarily susceptible to these errors and can, in some cases, exploit these errors. We're also going to discuss how images are formed. So this here is an image of a dark chamber or a camera obscura. So this is the very sort of first ideas of a camera from hundreds of years ago. And in this module, we're going to study how cameras work. We're going to study lenses. We're going to study projection. We're going to study distortion, why parallel lines seem to converge in images. And by understanding these things, we can understand depth estimation and how to measure distances in images, which really serve the foundation of autonomous vehicles, but also of augmented and virtual reality. So as computer scientists working in image and video analysis, we have a whole host of, or a whole suite of tools that are available to us. I'm just going to quickly mention a couple of those tools here. So on the left, we have an image of a cameraman. And then on the right, we have two different images. And both of these images are after filtering. So it's exactly the same as the sort of Instagram filters that you use, where you apply a filter and you see a slightly different version of the image. So we take this image and we apply, in the middle case, a Sobel operator or a Sobel filter. And this is essentially a matrix that we multiply through by the image in a sliding window fashion. And we get this sort of output, which looks like a series of contours or edges. So this Sobel filter, actually detects these edges. And on the right, you can see we've got a similar filter, which is called the Laplacian filter. And both of these filters here are approximations of first and second derivatives, respectively. And actually, these sort of filters form the basis of lots of image analysis techniques and of convolutional neural networks downstream with deep learning. I've also got a nice example here with my cat on the left that was taken relatively recently. and of my cat when he was a kitten about 5 years ago on the right. And if you were to try and teach a computer what a cat looked like, there are certain features that you might pull out. So for instance, you might say they've got pointy ears in both cases. So you can say maybe their mouth or their nose. These are quite distinctive points. And we can use algorithms such as SIFT that can automatically detect these sort of features or key points. And they're based on detecting features that have really big changes in intensity, such as corners, which these sort of ears are and the mouth are. And we can then actually match up images and use this to detect when an image is a cat or to match up corresponding images. And you can actually think, if we were for other applications, you can choose this for stitching together images to generate panoramas. For instance, that's exactly what you're doing on your phone when you're taking these sort of panoramic shots. But moving past these sort of traditional image analysis techniques, we've now got lots of deep learning-based techniques, or AI. And this is an example here of a convolutional neural network, or a CNN. And a CNN takes in an input image, so in this case, an input image of a car. It then applies a series of filters, so just like those Sobel filters that we discussed, or the Laplace filters. And then it outputs a classification. So it might say it's a car, or it can actually output a segmentation map, so a line around the car. And what's really amazing about deep learning and these CNNs is that we provide the algorithm with training data, so that's images and labels, and then it learns which filters are best in order to arrive at the final task at hand. So, for instance, like these Sobel filters. So here we've got another model. This is a deep learning model that was introduced by Meta AI, and it's called SAM, or Segment Anything Model. And what you can see here is that you essentially just click anywhere on the image, and it manages to detect and to segment the whole of that particular object. So you can see a snail, you can see a frog, you can see a turtle or a tortoise, and you can see the water around it as well. And in this module, we're going to discuss how these sort of models work. We're going to discuss how very similar models work as well. And we're going to discuss their limitations. We're going to discuss why you can do this sort of task with deep learning and why you wouldn't be able to do that with classical sort of techniques. And we're going to discuss a lot of the exciting applications of this sort of technology. A nice application is this. So we've got in the middle, you'll recognize Van Gogh's Starry Night. And on the left, you can see an image with some houses around a canal or a river. And we have this technique called style transfer, which can blend together different images. So here we can, if you look on the output after the style transfer, you can see we have this photograph on the left, which now looks like a painting that's been done by Van Gogh. So a really cool application, but has, of course, some really important legal and ethical considerations. Another really cool application is computational pathology. So this is actually my own area of research, and this is some of my research here. And computational pathology is a branch of medical imaging, and it's about developing algorithms that can help clinicians with diagnosis and also with prognosis. So this is an example from my work. This is about a disease, oral dysplasia, which is a precancerous disease that might become cancerous in the future. And in clinic, a clinician will take a biopsy of this, and then a pathologist will look at this underneath a microscope to come up with a diagnosis and to determine some sort of treatment. What we've done is we've digitized these images, and we've then segmented different structures in these really high resolution images, such as nuclei, tissue, etc. And then we've used these to determine when we think, using machine learning or artificial intelligence, whether the case will progress to cancer or not in the future. And actually, in this work, we found that our method can work just as well as a pathologist for this prediction task, or even slightly better in some cases. So a really exciting application here. Another application is, of course, autonomous driving, where deep learning can be used to detect the lane in front of you, but also to detect the scene around you. So different cars, different motorbikes, pedestrians, of course, traffic lights, detect what color the traffic lights are, the road signs. So all really important applications here. So hopefully what you've seen from this talk is that image and video analysis is a really, really important module, as it sort of sets the foundations for a whole host of really exciting applications in healthcare, in the automotive industry, in medicine, in gaming and in entertainment, in agriculture, and pretty much every domain you can imagine it's already being used in. So thank you very much, everyone.